Okay, this is exam 2 for physics 202, spring 2017. It's covering chapters 1.5 through 2. Consider this question of charges. Which of these statements best describe the net electric flux? Well, look, I have a net negative charge in here, the plus 2 and minus 3q, so that means that the net flux is also negative. That means that there's more electric field lines going in than there are coming out. The amount of electric field passing through a surface, that's called the electric flux. Which of these is a conservative force, electric force, gravitational force? So B is the right answer. Vectors represent the electric field. They're all the same length. What type of charge does the box contain? Let's see, I have 2 going in and 2 coming out. That means I have a net electric flux equal to 0 because I have equal numbers of E dot dA coming in and out. Positive and negative, that means there's no net charge. Electric potential is a measure of energy per charge. This particle is moving along an electric field. How much work is done to move the particle? Well, because the force on the particle due to the electric field is in this direction, and it is moving in a displacement in this direction, it has 0 work. They're perpendicular, it's dot product. You release proton, that's a positive particle at point A. What would the particle do? Well, positive particles move from high to low potential, so it will move to the left. Where on this line is the potential equal to 0? The potential is equal to 0, let's see, right here, because these two are equidistant apart, these two are equidistant apart, and these two are equidistant from that point. Whereas at other points on this line, say for example here, this distance is not the same as that distance. And you can see that's true for all the other points. So B is the right answer. Parallel plate capacitor is connected to the battery, has a charge of 10 coulombs. If you now double the plates, what happens to the value of the new charge? Well, capacitance is given by this. If I double this, I double this, and since Q is equal to CV, if I double this, I double the charge. So where it was 10 coulombs, now it's 20 coulombs. What must be done to increase the amount of charge a capacitor can hold? Well, if I increase the area of the plates, remember I have A over D, kappa, epsilon naught. If I increase the area of the plates, that increases the capacitance. If I decrease the separation of the plates, that also increases the capacitance. And if I insert a dielectric, if I increase the separation, that decreases the capacitance. So it's 1, 2, and 3. So to the circuit, all 3 capacitors are identical. What is the voltage across C1? Well, look, I got a C and a 3C here. I have 12 volts. I know that these voltages here have to add up to equal to 12, and that this one will have 3 times the voltage of this one, so that's going to be 9 volts and 3 volts. If you want to just put in a number for C, you can. You could do 1 microfarad to 3 microfarads and figure out the net charge. But it's easier just to think about how the voltages are distributed. Remember, the smaller capacitor has the larger voltage, so I'm looking for C1, so that's E. What is the primary purpose of a capacitor? Store electrical energy, kind of like the battery that we saw. What are you? Not just a student, though you are a student, not a paycheck, but you know, they do pay me to be here. You're certainly not an obstacle, but you really are the best students at Nichols, so I'm glad for that. It's fun to teach you. All right, what are the charge and voltage for each capacitor here? Okay, well, first we just want to redraw this. So I'm going to start on my 12-volt battery going in this direction. Notice I have a break here, so I have 2 parallel branches that have C1 and C2 in them. That's 2 and 4 microfarads. And then it comes back together right here, and then I have C3, and then I have another break right here where I have C4, 5, and 6. C4 and C5 are in series, C6 is in parallel with that, and then it all comes back. So it's right in my 4 microfarads, 4, 4, and 10 microfarads. So to find the equivalent, these two are equivalent 1 over 4 plus 1 over 4, that's equal to 2. So I have 2 and 4, this is 2 microfarads. So 2 and 4 give me 6, 4, and 12. 6 microfarads, 4 microfarads, and 12 microfarads. And then that equivalent is, well, let's see, 1 over 1 over 6 plus 1 over 4 plus 1 over 12. Find a common denominator. That would be 2 over 12 plus 3 over 12 plus 1 over 12. That's 6 over 12. 1 over a half. That's equal to 2. So I have 2 microfarads, 12 volts, I think. Yeah, 12 volts. All right, now I want to figure out the voltage on each capacitor. I know that this has Q equals CV charge, so it's 24 microcoulombs. So that means I have 24 microcoulombs here, 24 microcoulombs here, and 24 microcoulombs here. Now I can find out the voltage. Voltage is equal to what? Q divided by C. So 24 over 6 is 4 volts, 6 volts, 2 volts. And notice that that adds up to equal to 12 volts, as it should. So now I can begin to distribute these. I now have 6 volts here. These two are in parallel, so they're both going to have 4 volts and 4 volts. This one's going to have 2 volts. And these two are in series, but they're identical, so it splits that voltage identically. So that's it. That's the answers. I can write down all my voltages here. C1 and C2 are both 4. C3 was 6 volts. 4 and 5 are 1 volt, 1 volt, and 2 volts. And then, let's see, my equivalent was 2 microfarads. And then Q1, Q is just equal to C times V. So 4 times 2 is 8 microcoulombs. 4 times 4 is 16 microcoulombs. 6 times 4 is 24 microcoulombs. 1 and 1 times 4 and 4. Those are identical. And then 2 times 10 is 20 microcoulombs. Notice that these 20 and 4, that adds up to equal to 24, which was the same as the charge here. And likewise, 8 and 16 here and here also adds up to 24, because we didn't really use this rule, but the charges on parallel capacitors add up to equal the total charge. And that's it for that question. Draw 5 equal potential lines. Really just got to make sure that you get the line perpendicular at each point. So right here is just a circle. Just keep them perpendicular at each point. As you get further away from these, notice these are both positive, they'll just begin to look like a point charge. So the equal potential lines will begin to encapsulate both charges. And I'll leave you to do the rest of those, but you can add in a couple more. Here I have a potential described by this function. What is the electric field in vector notation? So I want to find my electric field is equal to negative del V. That is just the, excuse me, it's the partial derivative with respect to x, y, and z. So let's do Ex, negative del V del x. That's the derivative of this with respect to x. That's going to be 0, so it's going to be 3yz squared. Putting in my values for x, y, and z, I get that to be negative 12. What I did is I put in y equal 1 and z equal 2. 3 times 1 times 4 is equal to negative 12. And then I'll do a similar thing for ey. That's going to be equal to negative 2 plus, excuse me, 3xz squared in the parentheses. That's the the derivative with respect to y. And putting in the value for x and z, I get negative 2 minus 0, which of course is negative 2. So that's the y component, and now the z component. That's equal to 0 because x was equal to 0. So now the electric field is negative 12I minus 2J plus 0K, or you can leave off the 0K if you like. I think that was all I asked, yes. Okay, here I want to know what is the potential at point A, at this point right here. So to know that potential, I need to know the potential due to this charge and to this charge. So the total potential is sum of all the individual potentials. That's going to be kq over r, 9 times 10 to the ninth, 8 times 10 to the minus 9, divided by r, which is 4, plus 9 times 10 to the ninth, negative 3 times 10 to the minus 9, divided by 3. Now I can cancel some things. I'm going to change colors here. I'll cancel this and this, and this leaves me 2. So that's 18. This and this and this, minus 9. So it's 9 volts. And now how much work does it require to bring a 2 coulomb charge to point A? Well, work is equal to Q delta V, which is equal to 2 coulombs. The final voltage is 9 volts. The initial voltage is 0 volts, right? Because I'm going from over here where the voltage is equal to 0 volts, and I'm moving this particle over to here. So I can find that is 18 joules. Remember, volts is a joule per coulomb. You build a capacitor out of 2 metal plates. There's the area. What is the separation between these plates? Okay, so first, C is equal to epsilon naught A over D. Just sort of plugging in the right things here. If I solve this for D, I get 3.1 times 10 to the minus 9 meters. So 3 nanometers. And then if I insert a dielectric, what is the new capacitance? So C is equal to kappa of the times the original capacitance. That's 2 times 60 times 10 to the minus 15 farads. That's 120 times 10 to the minus 15 farads. And then how much energy is stored? This is the one without a dielectric. The energy is 1/2 CV squared. (4.3 times 10 to the minus 12). All right, here's an electric field given by this. I want to find what is the electric flux through the Gaussian surface, and then there is some mystery charge inside of that surface. I want to know what is that mystery charge, what is the value for it. Okay, so first let's just break it up into the top, bottom, right, left, front, and back, and you'll see that some of these will go to 0, but first let's do the top. The electric flux is the surface integral of E dot dA. So that is negative 2I plus 4yj dotted with 15j. Because on the top, that is 3 times 5. That is my area. And that gives me 60y. Because the only thing that contributes to that dot product is this. The I dot j is equal to 0. Actually, it's like it gives me negative 60y. So that is equal to negative 180 because y is equal to 3. That's in Newton meters squared per coulomb. It's a unit for flux. Newtons per coulomb, remember, is electric field times meter squared. Now let's do bottom. It's going to be identical, except it's going to be plus 60y. The reason is that my area here is now going to be in the negative direction because the area in the bottom points in this direction. But it doesn't really matter because y is equal to 0, so the bottom is equal to 0. Now let's do the right. Negative 2I plus 4yj dotted with 15. Oh, actually, let's see, I made a mistake here. The right is over here. It's going to be times 9I. My area vector here has a value equal to 9. That's 3 times 3, which is 9I. So it's going to be negative 18I. And then the left, the left is going to be equal to positive 18I, because everything's the same except for the direction of the area vector. So you see the right and the left, they cancel out. And then the front and the back, let's treat these together. They cancel out because, or they don't cancel out, they both have the flux equal to 0 because um, the electric field, notice, has no k components, and the area vectors for the front and the back are both in the k direction, so the dot product goes to 0. All right, now we add all these up. Notice that these cancel, and I'm just left with negative 180. Isn't that right? Yep. So the sum of all those fluxes is negative 180. So that's one of my answers. And then I also want to know, what is the charge enclosed? Well, the charge enclosed is equal to epsilon naught times phi, which is negative 1.6 times 10 to the minus 9 coulombs, so 1.6 nanocoulombs. All right, looks like that's it.